G'day chemistry students. In this video, we'll be looking at dot points 5.3, point 2, and 3. In particular, our focus is going to be on how we can use Keq to solve different problems and to learn about our particular equilibrium systems. So in this video, we're going to be looking at comparing Keq to Q values. We talked briefly about what Q is a couple of videos ago, but we'll be going into that in a lot more detail. And at the end of the video, we're also going to be talking about how the temperature of an equilibrium system, and in particular changing temperatures, can alter the Keq value of an equilibrium system. Let's get into it. What I want to talk about first and what I want to unpack is how the size of a Keq value, just the raw number, can give us some information about the equilibrium that it's describing. So the size of the Keq depends on the ratio of the products and reactants which are in equilibrium. And so we've got our ratio that comes from the fraction that we use to calculate Keq, whether our products are on the top and our reactant concentrations are on the bottom, depending on how many products there are, depending on how many reactants there are once the system reaches equilibrium. That's going to greatly impact our Keq value. For high concentrations of reactants, low concentrations of products, we're going to end up with a low Keq value. And I usually like to just substitute in some simple random numbers to sort of emphasize this concept. So low product concentration versus higher reactant concentration means little number divided by bigger number, and we end up with a low value at the end. On the flip side though, if we have a low amount of reactants and a high amount of products, we're going to end up with a high Keq value. The bigger number is going to be on the top, the lower number is going to be on the bottom. We end up with this big number at the end. And so we can use this concept in a few different ways when looking at our Keq applications. This is just a little bit more of a detailed explanation or set of general rules that come from your textbook. When we have big Keq values, usually bigger than 10 to the 3, that means that most of the substances present are going to be the products, and there's only going to be a few reactants present in comparison. But on the flip side, if we have a Keq value that's really small, say 10 to the negative 3 or less, that means that our equilibrium is sitting on the left, meaning the left side of the equation where there are going to be lots of reactants. So some products have formed in the process, but mostly there are going to be reactants in the reaction vessel. For values of Keq that are at 1 or thereabouts, that generally means that there's going to be a pretty even split of reactants and products at equilibrium. The numbers that they've given here are very generalized and are just estimates. They're not hard rules, but they, I guess, help to show you the scales when we're looking at Keq values. So the big activity for today is going to be looking at comparing Keq and Q values. We can calculate a Keq or calculate a Q value in the same way. We write up an equilibrium expression for the reaction that we're looking at. And the only difference between Keq and Q is that substituted concentrations for Keq are for concentrations at equilibrium specifically, no exceptions. Whereas for Q, when we're calculating that, we can be putting in concentrations when the system is at any point. So Q is really powerful because you can use it to see where a system is progressing through a reaction. Is it at equilibrium yet? Is it approaching equilibrium? How close is it? All that sort of stuff. So if you can take a snapshot of a chemical system, find all of its concentrations, you can plug in all of those numbers to figure out what this Q value will be at any given time. We can compare this to our Keq value to see what point we are at in the reaction. So for Keq, just to rehash as well, it's a constant, it's a known value that can be experimentally found. You won't find Keqs in your data sheet. They get given to you in context for every question where you are doing a Keq calculation. And when you're doing a Keq calculation, it changes depending on what type of reaction we're doing. So is it the Haber process? Is it our nitrogen dioxide reaction that we're always doing? But as well, it is dependent on temperature, which I'll talk about at the end of this video. So when you're comparing KEQ and Q, if you find that Q and KEQ are the same, this means that the system is at equilibrium. It's exactly where it's meant to be. And so what that means is that for the concentration of all the substances that you use to calculate Q, they are at the right concentrations. The reaction rate of the forward and reverse process are the same. However, if Q is not equal to KEQ, what that tells us is there's either too many reactants still present and the forward reaction needs to continue happening until there's the right balance, or there might be too many products and the reverse reaction needs to keep occurring until there's a balance of reactants and products. So using this very similar logic that I just used to explain how the value of KEQ could be low or high, we can use that same kind of concept to talk about Q versus KEQ here. So if Q is lower than the KEQ, that means that the system is not at equilibrium. And if Q is low, that means that there are too little products and too many reactants. What that's going to mean is that there's going to be a right shift, a favoring of the forward reaction until equilibrium is reached. And the opposite is true when Q is too big, when it's larger than KEQ. If there is a high Q value here, that means that there are too many products and not enough reactants, meaning that there's going to be a left shift. The reverse reaction will be favored and will keep being favored until equilibrium is reached. So using that idea, what we can begin to do are KEQ versus Q calculations. It's very similar to the KEQ calculations that we have done already. The steps are very similar as well. We need to identify the balanced chemical equation, write up the equilibrium expression, make sure that we know the concentrations of all the chemicals that have been measured. So that's not necessarily at equilibrium, but whatever the chemical concentrations are for the Q that we're trying to find. We then put those substitutions in to find Q, and we can compare Q to whatever KEQ has been given to us in the question, remembering that we're not going to find those KEQ values in a data sheet or anything like that. What we can then do is figure out, well, is the reaction in equilibrium or not? And if it's not, what direction will it proceed in? And that comes back to these ideas that are here and the three different outcomes that we can have for Q versus KEQ. From there, we can then also make a prediction. Let's get into this practice question that I've got prepared for this video. So in this video's practice question, we are looking at the Haber process. It's an important industrial process because it is used to synthesize ammonia from hydrogen and nitrogen according to the following equation. N2 plus 3H2 is in equilibrium with 2 lots of ammonia. And so at 427 degrees Celsius, the equilibrium constant for the production of ammonia is 0.26. And we're being told that the reaction takes place in a 4-litre flask and that during this process, measurements were taken and it was found that there was 1 mole of ammonia, 10 moles of hydrogen and 15 moles of nitrogen present. And in this question, we're being asked whether or not the reaction is in equilibrium or not, and if it isn't, which direction will the reaction proceed? So in this, we're going to be doing a KEQ versus Q calculation. Once we are able to compare those two values, we can then decide whether we're in equilibrium or not, and then also make a prediction on the outcome of the reaction. So we're going to run through our steps to be able to get to that point. The first thing that we need to do is identify the balanced chemical equation. That one's there. And using that information, we can then write up an equilibrium expression. So we're going to do that next. So we're going to put our products on top first. So the concentration of our ammonia gas, we're going to raise that to the power of 2. So when we're doing any of these calculations, this could be used for KEQ or Q values. We're going to do the denominator as well. So that's going to be all of our reactants. Notice as well that for the hydrogen, I'm going to put an index of 3 to match the coefficient in the reaction. The next thing that we need to do is identify concentrations of chemicals given. So we haven't been given concentrations here, we've been given N values. And we've been given the volume of the flask. So we're going to use that information to find the concentrations using C equals N over V. Just going to draw up a quick short table. So we're going to do this for the ammonia, the hydrogen, and the nitrogen. So we've got 1 mole, 10 moles, and 15 moles. So we're going to be doing 1 over 4, 10 over 4, 15 over 4 to get our concentrations. So that's 0.25, 2.5, and 3.75 moles per litre. Once we've done that, we can then go on to our next step, which is to substitute the concentrations to calculate Q. So I'm going to do that underneath here. So our Q value for this one is going to be 0.25 squared divided by 3.75 times 2.5 cubed. So I'm going to put all of that into my calculator, and that is 1.07 times 10 to the negative 3. The next step is to compare Q to the Keq given. So we've been given Keq and we have calculated Q. So what we can see here is that 0.26 is greater than 1.07 times 10 to the negative 3. And what that means is that the Keq value is going to be greater than the Q value. What we know from this is that if that's the case, we have a low product concentration and a high reactant concentration. If that's the case, that's going to mean that there will be a right shift. And if there's a right shift, that means that the forward reaction will be favored. And there we go, a solution to this question. We've been able to use our Q value to determine whether or not our system was at equilibrium, and because it wasn't, we could then also make a prediction on the direction of the reaction. To finish off this video, I just want to have a quick look at Keq versus temperature. We've talked about it a couple of times over the last couple of lessons, but I want to just emphasize some of those key points really clearly and succinctly. So we've already looked at Le Chatelier's principle before, and it says that if there's a change to temperature, that the system is going to either do the forward reaction or the reverse reaction to counter that change. So if I increase temperature, for example, the endothermic reaction is going to be favored to absorb that added energy. And this adjustment, what it does is causes a change in the product and reactant concentration. So if you have a favored reaction because of a temperature change, that's going to change the concentration of the products and the reactants. And as a result, based on everything that we've looked at so far, we know that for these Keqs, that they are completely dependent on product and reactant concentration. So if that's the case, if we're changing our product and reactant concentration, we're going to end up with a different Keq value. So for example, if I have this reaction, or it's got its enthalpy here, what that means is that we can calculate a Keq value for this reaction at 0 degrees, at 25 degrees, and 150 degrees, and those Keq values are going to be different every single time. So I want to emphasize as well the idea that when we're looking at temperature changes and Keq values and stuff like that, we don't need to take that into account when completing calculations. It's not within the scope of this course. All you need to have an understanding of is the qualitative effect of how temperature will influence Keq values. That's all. Thank you very much, everyone. In the next video, what we're going to be doing is sort of flipping these problem-solving questions that we've been doing. We're going to be given Keq values, and from that, calculate unknown concentrations. So kind of the reverse process of the problem-solving that we've done already. But until then, have a good one.